Hi everyone, Mrs. Hanson here. Today we're beginning a lesson in Chapter 5, taking a next step with stereochemistry and stereoisomers, our investigation of chiral compounds and the handedness that they exhibit. So welcome to the beginning of Chapter 5. Looking at our journey through the chapter, we begin with an overview of what isomers are. Isomers we have explored so far include constitutional isomers and stereoisomers. We'll learn about the cis-trans configuration that we began studying in Chapter 4 in cyclohexanes with the equatorial and axial positions of bonds on the cyclic 6-ring member. And we'll also bring in the cis-trans configuration of an alkene with a double bond. Both of those are examples of stereoisomers. But we'll also learn about chiral centers. Chiral centers are carbons, or any atom, but carbon specifically, that have 4 unique groups attached to them, and thus have a chiral center. We'll notice that they are different isomers because they are non-superimposable mirror images. We'll designate the Kohn-Ingold Prelog system of naming using an R and S configuration when naming chiral carbons. We'll talk about optical activity and chiral molecules that have the ability to rotate light. I'm letting you know that in section 5.4, our text includes calculations, but I am not going to test over the optical activity formulas. No math required in section 4 as presented in the text. Finally, we'll turn our attention to non-superimposable mirror images called enantiomers, and those molecules with chiral centers who are not mirror images called diastereomers. We'll look at symmetry and chirality and what we refer to as a meso compound, M-E-S-O, a meso compound having a plane of symmetry. We'll look at Fischer projections. Those molecules, again, represented in a 3-dimensional way other than dashes and wedges. And we'll conclude our chapter together in the video lessons with the nomenclature for alkenes, that should be the EZ designation for the diastereomers of alkenes. So let's begin by kind of getting a handle of an isomer. Isomers are different compounds. They have the same molecular formula, but there we'll see that they have 2 general types of isomers. In a constitutional isomer, we have the same molecular formula, but they're connected in a different order. For example, dimethyl ether. Notice that functional group ether has an oxygen as part of the long chain, and on either side we would see a methyl group, dimethyl ether, the name of a compound that has a molecular formula, C2H6O. We can reorganize the connectivity of those 2 carbons, 6 hydrogens, and oxygen by creating another conformer here known as ethanol, a functional group of an alcohol. Notice that we still have the same number of carbon, same number of hydrogens, CH3CH2OH, this functional group of an alcohol. This functional group is an ether. Same number of atoms, different connectivity makes for a constitutional isomer. We also will introduce and spend more time with what we refer to as stereoisomers. These also have the same molecular formula, but rather than a different connectivity, they are connected in the absolute same order, but just a different 3-dimensional spatial arrangement of atoms. For example, in our last chapter, we talked about cyclohexane, and if I were to draw what we referred to as a Haworth projection, a 6-cyclic ring, knowing that this is coming up out of the page because it is a bent area of the molecule, a Haworth projection. Notice that I could place, let's say for example, a methyl group on the top part of the molecule and a second methyl group on that particular carbon, but both are above the ring. And in terms of the plane of the ring, if they're on the same side, we call that a cis configuration, same side. If I make that reference again to a second Haworth projection of a cyclohexane, and again, I'm trying to show that those are wedges coming up out of the page. At position 1, if I had a methyl group pointing above the plane of the ring, and on carbon 3, a methyl group below the carbon ring, the chain there, this we call the trans configuration. The cis-trans configuration of 1,3-dimethyl cyclohexane. Notice that they have different names, and therefore they are different stereoisomers. And it became part of the structure's name, cis 1,3 dimethyl cyclohexane. Over here, coming part of the name is trans 1,3 dimethyl cyclohexane. Since they are different structures, they have different names. They are stereoisomers. Cyclohexane. I'm trying to spell and talk. Here we go. So what about a different type of stereoisomer using an alkene? Now remember, an alkene has a pi bond, and a pi bond in a double bond here is not free to rotate. Like a sigma bond has complete freedom to rotate, we do not have that same opportunity in an alkene. So just notice that those are fixed. They are not able to rotate. And so I say that because what if above the plane of the pi bond we place a methyl group, and on carbon 2 we place another methyl group, and down here would just be the hydrogens to create the tetravalent requirement of carbon. Notice that the pi bond has the methyl groups that lie above the plane of the molecule. This would also be a cis configuration. We'll learn to call this cis-2-butene. Now here's the critical part. This bond is not able to rotate. It is a very fixed position. So when I redraw the carbon-to-carbon double bond and I place a carbon above the plane of the double bond and the other carbon below the plane of the double bond, I have a new stereoisomer. One is above the plane, one is below the plane, and this would now be called the trans configuration. This is trans 2-butene. Now it's important to see that it is not achieved by rotating the double bond. This does not happen. Double bonds, triple bonds, do not have that same freedom of rotation as a sigma single bond. So in order to convert a cis to a trans configuration, it would require breaking a bond of the methyl group, breaking this bond of the CH group, and actually rejoining them to go from one conformation to the other. So the cis-trans configuration are not interchangeable. They are not interchangeable because the bond is not able to rotate. It's a very fixed, rigid area of the molecule. Since they have different connectivity in space, they are different stereoisomers, and they will have different names. So all of that allowed us to review the term stereoisomer from what we've talked about thus far in a cis-trans configuration. So repeating, we practiced last chapter with cyclohexanes. In a Haworth projection, we had an opportunity to practice cis and trans if we have the plane of the cyclohexane and both of those substituent branches lie above the plane, or both could be below. We called that cis, cis, 1,2-dimethyl cyclohexane in this example. Or if the trans configuration shows the opposite, that in other words, one methyl group is above the plane and the other is below the plane of the cyclic structure, we call that a trans configuration. They are stereoisomers. They have unique IUPAC names, and the cis-trans become part of the structure's name. And we mentioned that that's the same for a butene or any alkene. I drew 2-butene in the cis conformation, and I do trans 2-butene, having a group that's above and below the plane of the molecule. So think of this double bond as a plane, and if one lies above as the other does, that's the cis conformation. If one's above and the other's below, that's a trans conformation. Pi bonds do not rotate. It is not being achieved by twirling that bond. Convince yourself by building the molecule with your molecular model kit. Double bonds are impossible to rotate. So a review of isomers. You're going to be asked, are these molecules the same, identical structures, or are they constitutional isomers, stereoisomers, or the same? Well, let's take a peek at what we have. Here is a molecule that is a 6-membered ring, and on carbon number 1, I missed that, that's not funny. Carbon 1, 2, 3, 4, 5, 6, that's a good repair. We see an alcohol functional group. Notice that we have 1 and then the alcohol group. Do I really need the number 1, or don't you already know that it is indeed cyclohexane-ol? That as soon as I had a substituent branch coming off of the 6-membered ring, it automatically became carbon 1, so I don't need to tell you that. Over here, the same idea, 6-membered ring, this is called cyclohexane-ol. There is no pi bond for interconverting. There is no second substituent to have to care about cis or trans. So because it has just one substituent, one branch, if you will, there is no cis or trans is impossible, because a cis and trans, I'm comparing the position of 2 substituent branches. So this is impossible to be a cis-trans configuration, which takes off the plate of stereoisomers. Constitutional isomers would have them connected in a different order, and that doesn't seem to be the case. They have the exact same name. These molecules are the same. They're identical. Let's go down to this particular, we'll go down here. Let's see what we have now. I have 1, 2, 3, 4, 5, 6. There's 6 carbons in that ring. On carbon 1 and carbon 2, we have a hydroxyl group. So I see right now 1, 2, and then I could put, in terms of the location of those alcohols, we're going to call that cyclohexane diol. There's an E, cyclohexane diol. At position 1, the hydroxyl group is pointing up above the plane of the ring. At position 2, this is an equatorial bond, but again in the up position. It's above the plane of the ring. Since this is up and carbon number 1 are both up, this is the cis conformation of 1, 2 cyclohexane diol. How about this guy? 1, 2, 3, 4, 5, 6 carbons in that ring, so it's the same number of carbons. But at position 1, do you notice that this is above the plane, and in position 2, this is below the plane, whereas on this example, they were both above the plane. So now all of a sudden, we have trans. It's still 1, 2 cyclohexane diol. But now since they're the opposite, we labeled this one trans. Since the cis conformation and the trans conformation are the very definition of stereoisomers, we're going to label those as stereoisomers. Well, let's take a peek here at the next one. We'll go working down the page. I have an ether group, don't I? And a cyclic structure, I have an ether group. so an ether functional group. The oxygen is part of the backbone of that carbon chain, part of the member of the ring, an ether. Here, this is called a ketone. The carbonyl carbon, C double bond O. Clearly, if the carbons in this are all single bonds leading to the oxygen, and now the functional group has become a ketone, they are not the same. Do they have the same number of carbons? 1, 2, 3, 4. They have the same carbon. They have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and an oxygen. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and an oxygen. They have the same molecular formula, but a different conductivity. They are constitutional isomers. Let's work the right-hand side examples, doing more of your homework problems. I'm going to give an order to find the longest carbon chain. And it looks like I can find the same here. 1, 2, 3, 4. This molecule is 2-methyl-2-butene. I want you to notice that since the carbon that's in the double bond, those are the 2 carbons in the double bond, 2 of them have the same attachment. That carbon at position 2 is the same attachment. It's leading to a methyl group on each side, right? They are the same. That makes cis and trans impossible, because I need unique attachments on the alkene, and there'll be more practice kind of near the end when we're naming the EZ system of alkenes. The end of this chapter will focus on alkenes specifically, but just notice that because if I interchange the carbons at carbon 1 here and the top one up there, I'm not making anything new. If I change these 2 positions with one another, I've not created any unique attachment there. So these again are the same compound, 2-methyl-2-butene. Now one more here. 1, 2, 3, 4, 5. 5 carbons. This would be 2-pentene. The carbon here is attached to a hydrogen and a carbon. So this has that opportunity to be trans. Do you see that? This is a trans configuration because the carbon in the double bond has its attachment leading down. The carbon in this side of the double bond has its attachment leading up. That's the opposite side of the pi bond. And so just think about, this is the line of symmetry. This would be the trans configuration. Trans 2-pentene. Now look, here we have the 2 carbons in the double bond, but now all of a sudden they lead out in the same direction. So this is the conformation known as cis 2-pentene. And what we've just determined, that they are stereoisomers. And those are the conclusions we made, that we had identical molecules when we came up with the exact same name, and we had stereoisomers when we could find cis and trans, and finally when we had completely different functional groups like the ether and the ketone, we called those constitutional isomers. This is so important. Let's practice another. Let's draw these on our paper and decide, are these cis, trans, or neither? Well, to meet the criteria of being a stereoisomer, the 2 carbons in the double bond, let's say for here and here, those are the 2 carbons in the double bond, have to have unique attachments. So in other words, this guy is leading out to a hydrogen, and this guy is leading out to a hydrogen. So this carbon is attached to a hydrogen and a methyl group. Those are different from each other. This carbon is attached to an ethyl group and a hydrogen. So those are indeed different from each other. So as I compare, one thing to consider is look at the two attachments. So let me just make that a different color. Let's say I want to compare H and I want to compare the methyl. Those cannot be the same in order to have a criteria of cis and trans. So when I cut the molecule kind of this way, left and right of the double bond, each carbon in the double bond has to have two unique attachments to itself to have a cis or trans opportunity. And clearly we see that this case does. And so when I find the two carbons in the double bond, I see that they have their branches both falling under the plane of the double bond. They're on the same side. So this is a cis conformation. 1, 2, 3, 4, 5. This would be named cis 2-pentene. 1, 2, 3, 4, 5, 6. Notice that the carbons in the double bond, in the cyclo group with the substituent branch, those are two centers there. The carbon in the plane of a cyclic structure is above, and as well as this is above. So that indeed, above the plane of the six-membered ring, both of them above, is the cis conformation. This would be cis 1, 2 hexane diol. I'm forgetting the cyclo part in there, didn't I? Did I do that earlier too? I got it, cyclo. Okay, I had a little moment of scared. Cyclo, yep, we remembered. Okay, so I just want to make sure that I remembered the prefix cyclo. And so we remembered that this would indeed be a cis conformation of 1, 2 cyclohexane diol. Now, here's the two carbons in the double bond. One of them is leading down, and the other attachment is leading up. So that indeed is a trans conformation. Think of that double bond. One is above the plane, one is below the plane. We have 1, 2, 3, 4, 5. That's trans 2-pentene. Here we have carbon 1, 2, 3, 4, 5, 6. That will be in a trans position. I can see one hydroxyl group above the ring and the other is below the ring. Trans 1, 2 cyclohexane diol. All one word, I just ran out of room. And you know what, how about right here? Do you see that this carbon in the double bond, there's the two carbons, however, this guy is the same attachment as this guy. So if I interchange them, I would not create anything new. So this molecule here is 2, just kind of leading out, 2-methyl 2-butene. No possibility for cis or trans, so this would be neither. And we recognize neither because carbon number 2 had two like groups. Interchanging them would not create any kind of different spatial arrangement. So we labeled them. Here's our check. Cis, cis, trans to the left, trans, and then neither to the right. These cis-trans isomers are only one type of isomer. There are other important stereochemical, stereoisomeric relationships. And to identify such stereoisomers, we begin to describe the term chiral, a chiral molecule. A chiral object is asymmetric, which means it is not the same as its mirror image. We call it non-superimposable. To test whether two objects are identical, or if they are non-superimposable mirror images, we see what lying the molecule on top of itself would create. And let's kind of demonstrate with a molecule. And if you have your model kits. I can't emphasize enough how building a model kit would be enormously helpful. So for example, let's take a carbon atom. These are just your little molecular models. I'm going to call the red ball oxygen, leading up in the same plane as an oxygen. In the same plane, I'm going to call that green atom a chlorine. Going behind the page is a hydrogen, and coming out of the page is a bromine. So I have the tetravalent carbon leading to 4 unique groups. That's the critical criteria of being a chiral center. A carbon with its 4 valent bond requirements, all leading to a unique group. When I draw its mirror image and just kind of draw its reflection, here's the carbon, still leading up in the same plane as oxygen. Drawing to the right of the plane, away from the mirror, is the chlorine. Closest to the mirror is still bromine, and still coming behind the mirror is your hydrogen. We drew the mirror image of the molecule with 4 unique attachments. Now, can you imagine picking this molecule up and overlaying it on top of that molecule? You're allowed to twist, spin, whatever it takes to try to line them up so that the white atom is on top of the white, the blue is on the blue, the green is on the green. I challenge you, and you'll find you can't do it. That when I overlay these, I would still have, if I get the red on top, and I could still even get the blue down here, but I would end up with the green over here, and I'd end up with the white over here, that I wouldn't be able to overlay those. Therefore, these are non-superimposable mirror images. There's a vocabulary word we're going to practice. They are known as enantiomers, non-superimposable mirror images. Chiral carbons, a central carbon with 4 unique attachments, will be known as a chiral center, making the molecule chiral. We'll see that those 4 attachments, in order of priority, will either spin left or right, clockwise or counterclockwise. Let me kind of emphasize before we go on to the slide what we're leading to in terms of naming. We'll learn that the highest priority on that chiral carbon is the atom with the biggest atomic number. The biggest atomic number between the 4 attachments. We have a hydrogen, we have an oxygen, we have a chlorine, we have a bromine. Those are the 4 attachments to the carbon center. Hydrogen has an atomic number of 1. Oxygen's atomic number is 8. Chlorine's atomic number is 17. And bromine's atomic number is 35. Just right off the periodic table, I'm finding the atomic number. Now, the top priority has the highest atomic number. The highest atomic number is priority 1. The second highest atomic number gets priority 2. The third highest atomic number gets priority 3. And the lowest atomic number gets priority 4. Here's what I mean. In assigning priorities, this blue atom representing bromine is priority 1. The second priority comes from chlorine. We're going to assign it priority 2. The third priority comes from oxygen. It gets assigned priority 3. I only need 3 numbers to connect to see which direction I spin. Connect those numbers in which direction you spin. In this first example, the priorities, the way they're attached to the central carbon, gives me a clockwise spin. We'll learn that a clockwise spin is going to be given the letter R in its designation. Now look what happened. When we connect the priorities in this direction, we spin in the opposite direction. That's a counterclockwise spin. And we will learn that that is an S configuration. These are stereoisomers. They are non-superimposable stereoisomers. They connect their atoms in the exact same way, but in a different spatial arrangement. One spins the priorities clockwise, The other spins the priorities counterclockwise. They are non-superimposable mirror images, the very definition of an enantiomer. The carbon in the center is a chiral carbon. It is attached to 4 unique groups. Now I've got to catch up my slides because we really did a lot of good work on that. So let's emphasize some things we said. Chirality is found in molecules. And the reason we find it so important, one application especially, is in pharmacology. When 2 chiral molecules have identical properties, except for being enantiomers, they are not identical in the way they go through biomolecule pathways in our bodies. That the pharmacology, depending if the priorities spin right, clockwise, or left, counterclockwise, are they an R or an S configuration? That they have very different outcomes in biomolecule pathways. And perhaps one of the most newsworthy items of learning this lesson was in the 1960s with a drug called thalidomide. In the 1960s, a drug was marketed by the name of thalidomide and widely distributed throughout Western Europe. It was being prescribed to alleviate morning sickness. And you can see that there is a chiral center in that molecule, a stereocenter, a chiral carbon. It has 4 unique attachments. Thalidomide had previously been used in other countries as an antidepressant, and it was believed to be safe and effective for both purposes. However, it was never approved by the USA. It was not long before doctors realized there was something horribly wrong, as we noticed more and more babies being born to women who had been on thalidomide were suffering severe birth defects, truncated limbs. You can see the number of digits here and is a very significant indicator of a thalidomide baby. So the lesson learned was it was very important to synthesize this particular pharmaceutical drug with just one configuration of an R. And if the biomedical pharmaceutical company had a mixture of R and S configurations, if it was not purified, the S configuration had a horrible outcome, whereas the R configuration had no side effect at all. That the biomolecule pathway that thalidomide was involved in reacted perfectly in alleviating depression and morning sickness, but the same molecule, but with the opposite spin going in this direction, had a terrible outcome in the biomedical pathway. So chirality matters. And chirality is something studied enormously by the pharmaceutical companies to make sure that we have intended outcomes for chiral-centered molecules. So stereoisomers, these chiral centers occur when a carbon atom has 4 unique groups to the atoms. I said, let's let this represent a carbon atom. This would be a chlorine. Perhaps you want to let this one be bromine. This could be your hydrogen, this could be your oxygen, but we can clearly see that that is 4 unique groups. Draw a mirror image. The mirror image shows that the bromine lies closest to the mirror plane. Behind, still the hydrogen. There's the chlorine going down, and still in the same plane, the oxygen. We've drawn a mirror image. Now prove it to yourself that they are not the same. The order of priority. The carbon in the center has 4 unique attachments, right? One of the attachments is a hydrogen. One of the attachments is an oxygen. One of the attachments is a chlorine. And the other attachment, what did I miss? Bromine. Got them all, I believe. And so here all of a sudden, just making those groups up, I can say that spinning in order of priority, the heaviest, greatest atomic number, bromine, gets priority 1. Chlorine would get priority 2, the next highest atomic number. Priority 3 is the oxygen. Alrighty. So I'm going to spin, and I get a clockwise rotation. We'll learn to call that R. However, when I look at the opposite direction, priority 3 is the oxygen, chlorine is 2, bromine is 1. Now when I spin, I get a counterclockwise configuration. That's its enantiomer called the S configuration. Here's another example. Here we have a chiral carbon. In one direction it's attached to a hydroxyl. Here's a hydrogen. Here's a carbon. Here's a carbon to carbon. Now, you might want to argue that maybe those aren't unique groups because the carbons directly attached to that chiral carbon, are they the same or are they different? Well, the argument is you have to keep going until you find a point of difference. If there is a point of difference, they are not the same group. If there is never a point of difference, then they are the same group. So here I'm noticing that an ethyl group is not the same as a methyl group. Those are indeed 4 unique attachments. Look at the entire group attached to the chiral carbon. To find if it's the same or different, keep going to the next atom until you find a point of difference or not. The order of priority, we would have the oxygen with the highest atomic number, priority 1. The ethyl group, carbon to carbon, is of higher priority than a carbon to hydrogen, and the hydrogen then is last. We see a counterclockwise configuration. Spinning in this direction, we see the opposite. We would have a clockwise configuration. They are indeed mirror images. They are spinning their chiral attachments in an opposite direction, enantiomers. So let's just really emphasize the definitions of these terms. An achiral object means it's not chiral. It means that it has an identical mirror image. There's nothing unique about the structure to give it a right-hand or a left-handed configuration. So a glass sitting on a wooden box is an achiral object. However, think about your hands. A chiral object is one that cannot be superimposed upon its mirror image. Your hand reflects its mirror image, and yet when you try to lay a hand on top of each other, they don't line up. Your hand, as you lead towards your thumb on the left hand, would spin this direction, and as you lead towards your thumb from the opposite, it's spinning in the opposite direction. One spins left, one spins right. Clearly, if you have your palms up, overlay your hands, your thumbs do not line up. They are mirror images, but non-superimposable. So your hands are a chiral object. Molecules exhibit handedness as well. These molecules are indeed mirror images. So if I put a mirror right here, this is the reflection. I would say compound B is the mirror image of compound A. And yet, they are non-superimposable mirror images. Imagine just picking this molecule up and overlaying it on this side. Clearly, you would notice that the R's and the H's end up on opposite sides, non-superimposable mirror images. And you can prove yourself just by labeling the priority. Are they spinning the same direction? And at this point, since we have just kind of a general R, we could just label them in terms of priority arbitrarily. All that matters is that you label them the same on both images. When I connect the numbers in this direction, I get a clockwise spin. When I connect the numbers in this direction, I get a counterclockwise spin. That helps us prove that that is a chiral carbon, non-superimposable mirror images. They are known as enantiomers. You're going to work several problems where you're just looking at some structures, and some of them can be quite overwhelming, large structures with all kinds of things going on, and asked to identify how many chiral centers. One of the first strategies I would recommend that you use, find any carbon that is not an sp3 hybridized carbon. If you see any double bonds, right, those are sp2. If you see any triple bonds, If you see any triple bonds, C, triple bond C, that's an sp hybridized. To be a chiral center, you must be an sp3, 4 bonds from carbon. So that's mandatory. To have 4 unique attachments, they have to have 4 bonds. They have to be single bonds. So look what we're able to do with just that executive decision. I can eliminate any carbon that's involved in a multiple bond. All those carbons eliminated. All of these carbons eliminated. Those are all sp2 hybridized. Here's another carbon involved in a double bond. Get rid of them. Don't even bring your attention there. That helps to clearly focus on finding carbons with 4 attachments. So do you notice that once we eliminate all the noise of the double bonds, we have 2 sites left? That the carbons that have 4 unique attachments are now highlighted. Those carbons are sp3 hybridized and have 4 unique groups. Therefore, this molecule, with its complex structure, has 2 chiral carbons. When an atom forms a tetrahedral center with 4 different groups attached to it, it is now known as a chiral center. You need to analyze the attachments to determine if it is indeed a chiral center. So for instance, here we have a compound. I have a 1, 2, 3, 4 carbon chain. This would be named 2-chlorobutane. However, does it exhibit a chiral carbon? CHLOR, chlorocarbon. So keep in mind what's not shown but we know is there is a hydrogen. So we can see that in one attachment we have a chlorine, a second attachment a hydrogen, a third attachment is a methyl group, and a fourth attachment is an ethyl group. So they are indeed different. So thinking about attaching, the chiral center, carbon 2 is a chiral center. This carbon has a wedge of a chlorine, a dash of a hydrogen, methyl, ethyl. So priorities, carbon leading out to a chlorine. Chlorine has the highest atomic number, so that's priority 1. I have a carbon attached to 3 H's and a carbon attached to another carbon. That wins. The longer carbon chain is higher priority. And here, the methyl group is the 3rd priority. And remember, hydrogen with its atomic number 1 is always of lowest priority. I only need 3 numbers to spin, so this is going to spin in a clockwise motion. So we'll learn that that is the R configuration. Clockwise, a right rotation. So that is a chiral center. Here's a molecule, 1, 2, 3, 4, 5, 6 carbons long. And we have, what we'd named this so far is 3-hexane-ol with the alcohol ending, the OL ending for the alcohol. Now we have a chiral center. That chiral center contains 4 unique attachments. So the chiral center, I can see in one direction an ethyl group, and the other direction a propyl group. That's a 3-carbon chain. That's straightened automatically for me. It's 3-carbon chain. I see a hydroxyl group. That's different. And what's not drawn but we know is there is the hydrogen. And so I just draw that hydrogen in as the dash coming down the page there behind so we don't see it. But I do see 4 unique attachments. So that is indeed a chiral center. We'll learn that the top priority was the oxygen, the highest atomic number. The longer carbon chain is the next priority, then the ethyl. We're spinning in this direction. That is a counterclockwise direction. So that would be the S configuration. Here's a chiral center. That carbon is attached to a bromine and a hydrogen. Now watch carefully. I can see that this carbon next door is involved in a double bond. That makes it a different branch than a carbon that's involved in a single bond. So again, that is indeed a chiral center. It has 4 unique attachments. we'll also learn that a carbon-to-carbon double bond is of higher priority than a carbon-to-carbon single bond. That double bond counts carbon twice. Bromine would be priority 1, the double bonded carbon priority 2, carbon-to-carbon single bond priority 3, and that's spinning in this direction. That is the R configuration. How many chiral centers are in each of the following compounds? Pause the video and draw these in your notes and ask yourself to identify, maybe with a highlighter, how many chiral centers are there, and come back to the video when you're ready to check your work. Are you ready? Well, let's see what we found. We're practicing finding chiral centers. Clearly, I can eliminate any compound that has a CH2 group. Those are attached to 2 hydrogens, not chiral. Attached to 2 hydrogens, not chiral. All of those are quickly eliminated because I see that its attachment is to 2 H's. So I'm not even really interested there. So my eye goes right here first. I can see that we have a carbon attached to an OH. Not drawn, but we know is there, is a hydrogen. So those two are different. Now we have to decide if there's a point of difference. When I go to the left, oh, let me make that a different color. I go to the left, I get a CH2, I get a CH2. It's okay, so no point of difference. Let's keep going down the chain. Here and here. No difference, identical CH2s. As a matter of fact, I finally land at CH2. That the progression that I took going in this direction from this carbon and in this direction in this carbon led to no point of difference. I'm sorry, I keep doing that with my arm. Since there's no point of difference as I traveled in both directions along that cyclic structure, no point of difference, there is no chiral carbon. How about we'll go over across the page and we'll look at these examples. Let's examine these 2 carbons one at a time. Let's just examine the first. Let me highlight this. First one is yellow and see what it's attached to. So not drawn is a hydrogen. So let's call this carbon 1, shall we, at C1. One of the attachments is a hydrogen. Another attachment is the hydroxyl group. And then notice, we start trying to find a point of difference. So the first point of difference is 1 carbon away in the cyclic structure. Those are not equivalent. Do you see that? The carbon in this direction is attached to an OH group, and the carbon in this attachment is just attached to 2 hydrogens. So those are not the same. There is indeed a point of difference. So this, of course, represents a chiral carbon. And the same is true here. We could do the exact same lead work and end up with the same story. That is also a chiral carbon. We have 4 unique attachments. There is a point of difference in that cyclic structure. How about this? Oh my goodness. Let's examine this center first. Let's see what we have. In one direction, I have a carbon branch. That's 1 carbon before it branches, and then we have an ethyl group. So we have, thinking about this, is an ethyl length, 2 carbon chain, 1, 2. And if I go in the other direction, I can see that this is different because I have just 1 carbon, after the branch. That the carbon there is actually a methyl group. This is 2 carbons long, where this is 1, 2, 3 carbons long. So thinking about after the adjacent carbon, let's number those better. Just really want to emphasize that they are different. Let's point out, using a highlighter, how they're different. Carbon 1, and then the branch. So there's a total of 3 carbons adjacent to the left. Over here, there's a total of 4 carbons adjacent to the right. There's a total of 1 carbon adjacent down, and not drawn but we know is there is the hydrogen, making that a unique branch as well. So this right here is indeed a chiral carbon. Do you see another? How about this test? I mean, we've got this one labeled, but what about looking at the perspective of, let's say, how about this guy? I like that. How about you? This carbon is attached to a methyl, a CH3. It's attached to an ethyl, which is a CH2CH3. And then it's attached to a longer branch. This clearly is different. And it's got a hydrogen. Yeah, that is exactly chiral. So, all right, we've got 2 so far here, don't we? We've got 2 here and here. Let me ask you to consider that carbon. No, you didn't fall for that, right? Because these are identical groups, so that is not a chiral carbon. Our final answer just shows 2 chiral centers in that molecule. You get faster with these, don't you? I can check out this one really quick. Are those unique attachments? And even though it's not drawn, you know that there is a hydrogen there. So there is a 4th bond. So in one case, we have a direction that's a methyl group, Me for methyl. And in this direction, we have an ene. And in this direction, we have a branched ane. Those are 4 different groups. That definitely meets the criteria of a chiral center. Examine this one. Are those 4 unique attachments, knowing the 4th is a hydrogen? Absolutely they are. 4 unique attachments. A methyl, an ethyl, a hydrogen, and a long carbon chain. So that again has 2 chiral centers. How'd you do locating those? We decided the first had no chiral centers. The second had 2 chiral centers. The third had 2 chiral centers. And this also had 2 chiral centers. It's just a practice skill, and the more you practice, the faster you get at recognizing those. Can you find and label all of the chiral centers? This is one from your homework. It's a snapshot of vitamin D. So remember, you can get rid of any carbon that's involved in a double bond. So I'm going to highlight the ones to not consider. And that eliminates actually quite a few there. Don't consider the yellow ones because they're carbons that are in double bond. Another don't consider any carbons that have 2 hydrogens attached to them. They'll never be chiral. Any carbon that has 3 hydrogens attached to it will never be chiral. So that eliminates any kind of terminal end, as well as anyone that's in a cyclic ring without a substituent branch. Look at what we've done. We've eliminated all of those. And as a matter of fact, I can eliminate this guy because he has 2 like branches. He's leading up and down to methyl groups. All eliminated. This guy too, a terminal end. Well, what else does that leave us to examine? How about what we're going to highlight in blue? Is that a chiral center? Well, clearly I can see the attachments are an OH, an H, and let's look at point of difference. We have a CH2, that's the same, but keep going. Here's a CH2, here's just a CH. It's involved in a double bond. 1, 2, 3, there's no H on there at all. It's just a carbon that's tetravalent. So there is a point of difference. This is indeed a chiral center. 4 unique attachments. Let's examine what we'll call, how about orange? We'll pick orange and put one right there. Chiral or achiral? Do you see 4 unique attachments? This guy right here, he's got 1, 2, 3 bonds leading to very unique groups of carbons. And don't forget, he's got a hydrogen on to make that 4th bond. So yeah, what we just highlighted in orange is also a chiral center. And if we just keep that good work going, you begin to recognize quickly, here's another chiral center, that carbon right here, oops, I'm trying to highlight, that if we just pick out this carbon here, it has 4 unique attachments. How about here? Yes, 4 unique attachments. And even here, 4 unique attachments, absolutely. So we're getting better and better at recognizing which to eliminate and which to focus on. Any type of carbon that's in a double bond, get rid of it. Any type of carbon that is attached to a like substituent branch, get rid of it. Or if it has 2 or 3 hydrogens, get rid of it. When we come back to our next lesson, we're going to practice drawing enantiomers, those mirror images that are non-superimposable. Take a break, come back when ready.